In this series of videos, we're going to be covering some of the more advanced properties of cyclic groups. So we're not covering everything there is to know about cyclic groups, and assuming familiarity with the definition of a cyclic group and some comfort in playing around with examples of cyclic groups, but we'll be covering some of the more advanced properties and working towards the proof of the fundamental theorem of finite cyclic groups. I do want to start with an example. One example just to sort of notice some things and observe some things, but I also want to show you how to do a few things in Excel, which can speed up your time if you're trying to do some modular arithmetic computations. So the first thing I want to do is take a look at Z mod 12Z. Doing modular addition is not really that difficult by hand, but if you were working with something more complicated, it's nice to know just how to toy around with some things in Excel. So what I'd like to do is, using the group Z mod 12Z as an example, I'd like to go into Excel and walk through taking each individual element of Z mod 12 and looking at the different powers of that element, something that's somewhat difficult to pick up from a Cayley table. So let's go ahead and do that in Excel here. So pull up Excel. And now what I'm going to do is I'm going to come down here and put the elements of Z mod 12 as the rows here. And then what I'm going to do here is I'm going to, in the columns, sort of put the iterated power of an element, so to speak, here. So let's do the powers 1, 2. Let's go up to the size of our group, which is 12 things. And so what I will be putting here is I'm going to be doing modular arithmetic. So the command in Excel for that is mod. And what you do here is open the parentheses, and the number that you want to take comes first, and then the modulus comes second in the parentheses. So what I want to do is I want to consider 1 plus itself, and I'm modding by 12 since that's what's special here. Nothing really special is happening. 2 is just 2. I haven't had to do any sort of rolling over yet. The same thing would happen here with 3. Let's take 2 plus itself, modding by 12. And one thing that Excel is really great at is picking up on patterns. So what I can do is I can say I want to sort of repeat that idea as we go on down the line. And as we would expect, 5 plus 5 is 10. We haven't done any modding yet, but 6 plus 6 is 12, which mod 12 is actually 0. And 7 plus 7 is 14, which mod 12 is 2. So you see that this modular arithmetic seems to have been done properly here in Excel. And I guess really I have the columns sort of numbered wrong, incorrectly. So I'm going to make this little pattern with the columns here, and I'll drag that out. And then we should be good to go. I don't need that one. So what's going right here is sort of the number 1 squared is a way that I could think about it if I'm using a multiplicative notation, or the number 2 squared here. And that squaring just means perform that operation with n of the group elements. And so let's continue in this manner. Let's see if we can fix this all out. So what I would want to go in this spot in my table right here would be 1 plus 1 plus 1. So I would want mod the previous entry, which is 1 plus 1, and then one more of the element in question, always modding by 12. What I would want to go here, again, is using my modulus, the answer right here, 1 plus 1 plus 1, which is the element cubed, plus the group element, which is the entry right here, it's modding by 12, and so on and so forth. So you can see that what I always want in any particular entry in this matrix is I want the entry to the left to be added to sort of the first entry in that same row, and then I want the result to be modded out by 12. So the way that I'm going to do that for Excel is I'm going to enter in mod right here. I'm going to enter the previous value, so that's the power of this element, 1 power less, and then what I'm going to do is add on, and I want to indicate that I want the same row here I would like to A3. What that money sign in front of the A means is don't move that column. When I'm going to eventually take this pattern, sort of drag it to the other cells. And what I mean is don't adjust so that, for instance, I'm always adding things that are, 3 columns apart. What I want it to always be is the one before, and then the money sign is specifying I really want the column A, exactly the column A, and don't try and pattern match with that. Right? And this works perfectly here. Then what I'm going to do is drag this over all the way to the end. And again, 1 is a really nice easy number, so we can check that all the arithmetic is working as planned here. Now let's go and do that in this entry right here. So mod, what I want to do is take the previous entry, the one always to my left, and I do want that to change with me as I head down the row, just exactly one to my left, so the column is going to be changing, and what I want to add on to it is exactly column in A, but the same row that we're on. I want to be modding by 12. So just as we would expect, 2 plus 2 plus 2 is 6, just as we would want right here. And let's take this cell right here and drag the pattern out to the rest of the row. Good. And now that I've done that, in fact, I can do more than drag it to the rest of the row. Excel is really smart. I can take this one pattern for this cell and I can drag it, maybe not. Let's do one more. Mod, the number before us, plus money sign A. We're in row 5 now, always modding by 12. Now let's select these 2 entries right here in Excel, and let's drag that formula to be applied all the way throughout the rest of our table. And just like that, we have a table that what we're looking for. So again, what does this table do? What it gives at row n, column k, is the element n raised to the kth power. Again, using raised to the kth power, interpreting that in our group context here, that means performing that operation k times, which here is addition. And we'll notice some things that we'd like from this table. The reason I've done this is, okay, so we have seen right here that this group is in fact cyclic. This is a really great way to pick up on if a group is cyclic or not. So I found myself a generator, and that's the number 1. I knew that already for Z mod 12Z, but here's the number 1, and I can tell that it's a generator because I've looked at all of its powered, 1 to the first, 1 squared, 1 cubed, and so on, and I've gotten every single group element in this row. So that shows if every single element is in the entire group is a power of this one element, then I know that I've found a generator for the group Z mod 12Z. And what's great about this table is I could pick out if there happen to be any other generators, so I can see if I get rows, are there any other rows where I see every number from 0 to 11 inside that row. So that's definitely not the case for this row starting with 2. I've only got the evens here. Also not the case with 3, 3690, 3690 over and over again. Not the case with 4, but it is the case with 5. I've got all the numbers I could want here with the 5. Not the case with 6, definitely, 06, 06, 06. It is the case with 7. I do really and truly have every single number, 0 through 11, inside the row for 7. Not for 8, 9, or 10, but it is also the case with 11 that I've got every number from 0 to 11 inside that row. So I could go through from this table and I could pick out that there are exactly 4 generators for Z mod 12 under addition. They are 1, 5, 7, and 11, and that was something that I could determine from this nice little handy use of Excel. So let's return now to our slides. So the next thing that we have written here is that Z mod 12Z is a cyclic group, but in fact it has 4 generators, 1 and 11, which are sort of the easy generators to come up with on your own, but also 5 and 7. And what's great also about our table in Excel is if we stared at it a little bit longer, we would have noticed a lot more. So we would have noticed, for instance, that Z mod 12Z has 6 cyclic subgroups, and the orders of this cyclic subgroups are 1, 2, 3, 4, 6, and 12, which is kind of interesting. we're working in Z mod 12Z. We've got a group with 12 elements, and we've got a subgroup, a cyclic subgroup in fact, for each of the divisors of 12. Just something nice. And here I've listed out what they are. So if you'd like to go back in your own version of Excel and look at this more carefully, you could. So I've just taken, in order to find these, I've just taken every single element of the group, 0 through 11, and I just looked across that row at the corresponding entry to see what group it generated. So I found, obviously, when I take the group generated by the identity, all I get is the identity. When I take the group generated by 6, I saw that all across that row for 6, I just alternated back and forth, 0, 6, 0, 6, 0, 6. So the group generated by 6 is just the set containing those 2 points, and so on. And in this very last row, what we have here is just the fact that we noticed that 1, 5, 7, and 11 were the rows where we had all of the numbers 0 through 11 there, so we generated the whole group. Now, similarly, we could go into Excel and we could use a different group. Let's this time use the group U of 13. So remember, this is the set of positive integers less than 13 that are relatively prime to 13. Since 13 is prime, everything is going to be relatively prime to it, and so all of the numbers 1 through 12 belong to the group U of 13. Here, however, our group operation is different. Here, our group operation is modular multiplication, and what we're modding by is 13. So let's go and let's put this one into Excel, since this is actually a nice example where the computation is a little harder. Just go back into Excel, I'll add a new sheet, and I'll do something really similar. So I'll put the numbers 1 through 12 here along the row, and then I'll do powers of these, starting with the non-trivial. I guess if I'm in a pattern recognition, I could do that all the way. And we'll go up, I guess, to the 13th. No, we don't need the 13th power. And so 1 is the identity here. Now we're using multiplication, so 1 squared will just be 1, 1 cubed will just be 1, and so on and so forth. That's what I should expect to see in this row. But what I want to do as the entry in this row is, again, I'm going to be using modular arithmetic of some sort, and I want this cell multiplied by this cell. And this time what I'm modding by is 13, not 12, since we're in U of 13. And let's keep doing that. Mod this cell times this cell, mod 13. Nothing very interesting is happening here. 4 is the first place we should expect something interesting happen, and we can just check ourselves with easy enough computation to do. 4 times 4 is 16. We're modding by 13, so the answer that we should get here should be 3, and it is. So we're trusting that Excel is doing the thing we'd like it to, and we've kind of done enough on our own that Excel can do some pattern recognition. It can fill all these things in for us. So here we go. We can even fill in for 1 if we'd like. This is every element squared modulo 13. Okay, now let's use our pattern recognition again. Just as I did in the previous Excel document, I'm always using modular arithmetic, and what I want to do is I want to take the cell just to my very left, and I want to multiply it by the group element here, specifically the A, and I don't want that part to change, so I use that $sign. I'm always modding by 13, and I'll enter that here. It really is true that 2 cubed altogether is 8, so this seems to be working. Again, 2 to the 4th power is going to be the 8 times 2 is 16, so we should get a 3 here. Let's drag this pattern across our row and see what we find. And we do at least get the correct entry here. So we trust this and we pull the formula straight across in this row, and we've got this row of the table filled out. Let's one more time enter in, take the 9 here, multiply it by the 3. So always using row 4, fixing the A, and then allowing the column to the left to vary, always modding by 13. This is the formula that we'd like to use here. So we've got, again, this is a good value. 3 cubed is 27, and 26 is a multiple of 13, so we really should expect this to be 1. So I believe that entry. Now let's see if we can pull this formula that we've got all the way through the rest of the table, and bam, we're done. So just as we did with Z mod 12, now with a harder group, U of 13, we've got a really nice table here. Again, here's the group element in column A, and then it's raised to the kth power, the power that's listed up here in the top. And just for fun, let's pull this pattern all the way across to include the ones there, and we've got a nice complete table. So just like we did with Z mod 12, let's go through and see if we can find a generator for the whole group here. And we get really lucky. We find with the number 2 that we find every single element 1 through 12 inside this row. And so we see that U of 13 really is a cyclic group. It's generated, for instance, by the element 2. And if we go down and we check here, we see in fact that U of 13 is generated by 2, and just by running a check on the elements in each row, we see that this group is generated by 2, by 6, 7, and 11. Now we go back, perhaps a little bit less obvious, but we go back to our slides, and all I've done right here is I've summarized that entry for row 2 in the slide, so I have it and I can refer to it. And as we saw in our Excel spreadsheet, U of 13 has 4 generators. We saw that the rows where we saw all of the numbers 1 through 12 were the rows 2, 6, 11, and 7 table. And if we would have stared at that document a little bit longer, we would have noticed that U of 13, this group, this cyclic group that has 12 elements, also happens to have 6 cyclic subgroups. And the orders of those subgroups are 1, 2, 3, 4, 6, and 12. And you can list them out right here. And this is something you could easily check in your own version of Excel in this spreadsheet. And we've got what the groups are right here. So in this very last line, all of U of 13 is generated by 2, 6, 11, and 7. Now, back when we were working with Z mod 12Z, you might have noticed something interesting. So let me click back to that slide, for instance. The group that had order 2 was found by the element 6. And that's sort of interesting because 6 times 2 is equal to 12. And the group generated by the element 4 had 3 elements in it. And again, 4 times 3 is equal to 12. Similarly, the group generated by the element 3 had order 4. There are 4 things in that list. And 3 times 4 is equal to 12. So you see something really cool going on here with the arithmetic. Even though we're dealing with a cyclic group that has the same number of elements in it, it's much harder to notice a pattern in what's going on here if you're looking at the elements of U of 13. So first of all, there might be some confusion with what's important here is all of our computations are being done modulo 13, so it seems like 13 is this special number. And there's really no relationship between 1, 2, 3, 4, 6, and 12 and the number 13. Those are all numbers that are special to 12. So you might be kind of confused about that. But furthermore, you don't have this nice sort of multiplicative property. For instance, the group generated by 6 is the whole group instead of just this group of order 2. The group generated by 3 has 3 elements. The group generated by 4 has 6 elements. So you don't really seem to get any nice pattern recognition in this way, which you may have suspected from Z mod 12Z. However, if you use that a cyclic group has this special property that you really shouldn't be thinking about having, lots of different elements. You should be thinking about having one special element, which is your generator, and then the powers of that generator. If you rewrite everything in the group U of 13 according to what that number ought to look like as a power of 2, that's when you start to notice a pattern, which is really cool. So that's what I'm going to do on this next slide. I've retaken everything, and according to this chart that we have up here, I've written all the different numbers as how they are as powers of 2. So we saw that U of 13 had these 4 generators, 2, 6, 11, and 7, which really had no particular relationship with 12. But if I rewrite 6 as 2 to the 5th power, right here's 6, this is the 2 to the 5th power. 11 is the entry that appears here as 2 to the 7th modulo 13th, and 7 is 2 to the 11th, then what I have is that the 4 generators of u of 13 are 2 to the 1st, 2 to the 5th, 2 to the 7th, and 2 to the 11th. And if you'll recall, in Z mod 12Z, the generators of Z mod 12Z were 1, 5, 7, and 11. Similarly, we saw that the group generated by the number 6 in Z mod 12Z was a group of order 2. Here, it's the group generated by 12 is this element, this group of order 2, but 12 is really 2 raised to the 6th power. Similarly, it was the element 4 in Z mod 12Z that generated a group of order 3, and here it's the element 3 that generates a group of order 3, but 3 is really 2 to the 4th power. And so if you are willing to use this property that defines a cyclic group, namely every element of the group is a power of a generator, if you, instead of thinking of the numbers as a collection of 12 numbers themselves, if you think of them as just a whole bunch of powers of one number, you can start to notice the patterns and the similarities between this example in U of 13 and the more intuitive example of Z mod 12Z. And this pattern and this way of thinking is what really led to the proof of, and the pattern recognition that comes about from the fundamental theorem of finite cyclic groups, which is what we're working toward here.